Great, you can see your screen now. So we can perhaps get started now that it's being recorded as well. And so just to the audience, this talk is being recorded. After the talk and Q&A, we will have a discussion with Joe for the class students at the end. That part will not be recorded for public release, but the talk part and the Q&A part will be released on YouTube, which Joe has agreed to. Thank you, Joe. So again, welcome to the legendary Joseph Hellerstein from the University of California, Berkeley. So folks in the database world, everybody knows him. And he refuses to be boxed in on an area. So his expertise and his impact spans so many areas of computing and beyond that it'll take me forever to just list them. But it's an honor to have you, Joe. Welcome to UC San Diego. And you're going to be talking to us about some of your data engineering course materials from Berkeley's data science courses, right? So it's great to see both San Diego and Berkeley leading on this front on data science. And of course, we went our own department route. You're doing something else over there. We are keeping an eye, and I'm sure you're keeping an eye on us too. So it's great to exchange notes. So welcome again and take it away.
Thanks, Arun. My brother. So I should tell everybody, Arun and I share some academic lineage. We're both PhDs from the University of Wisconsin. So we were sort of brought up in the same soup. So if you see similarities in our worldviews, there may be a reason for that. And if you see differences in our worldviews, it might be because, I don't know, Arun's fresher and newer. We'll see. He's also very much his own man. All right, so what I'm going to do today is kind of give you a sampling of some of the topics we're covering in a new course we're just offering at Berkeley this spring for the first time. It's currently a 194, which means it's a little experimental. It's a little unpolished, but the goal is to compost this down into our data science curriculum. And I'm teaching it with my colleague Aditya Parameshwaran, who gets a lot of the credit for driving this agenda and for some of the content we'll see today. But mostly what we'll go through is a lecture that I've either presented or a lecture I'm presenting very soon in the class. So this is kind of torn from the pages of the class we're teaching. And it is a bit of a sampler. So I don't know in terms of the course that Arun's teaching, how this will fit in. And if there's things that you don't have the prerequisites for, I'll apologize. And if there's things that are familiar, I'll apologize for that as well. So just to give you a flavor, our data science program at Berkeley absolutely blew up. We've been kind of planning it for a bunch of years and starting to introduce courses. The major was actually officially opened in 2018. And because students had already been taking courses that qualified for the major requirements, we had graduates by 2019. There were over 100 majors graduating, which, for some schools would be a big number. For Berkeley, in UCS, for a UC, it's not a big number. But the pipeline is gigantic. So this is the Data 8 class you're seeing at the bottom of the screen. Back in the before times, I think that's John De Niro and David Wagner team teaching the class. And we have to hold it in the concert hall because it's too big. So we were getting over 1,500 students each semester. And the Data 100, which is the course you would take if you wanted to take another semester, and probably you're going to major, is over 1,000 students a semester. So I expect the major to be producing hundreds, if not over 1,000 students every year. Actually, if you multiply by 2, maybe up to 2,000 students a year. So it's a lot. And then, we're building out an organizational unit on campus, including a building, which we've started fundraising for. And the first dollop of money from anonymous donors there to build a place for everyone involved in computing, data science, and society to gather. So this is going to hold the departments of EECS, statistics, I think IEOR is possibly going to be in there, and then spaces for the domains of application to fit in as well. And our information school will also be in there. So it's going to be really a centerpiece of what Berkeley's about. So to get into the topic today, talking about data engineering in this new class, I've been on the curriculum committee for the data science program at Berkeley for some time, but I was the only sort of applied database person in the department and ECS at Berkeley for many, many years. And so I sort of held my tongue a bit in terms of pushing the curriculum towards things that I might teach because there weren't enough of me to cover them. And what evolved, and I think this is rather conventional, it's not just Berkeley, is a view that, this is what we teach in our Data 100 class, that data science involves a data scientist and a static data set kind of coming together in this happy way, where the data scientist employs some specific models they have in their toolkit on some predefined objective that they have for this data set. And the data set has been provided, in a nice form. It's clean, it's rectangular, so it's either like a matrix or a table, and it fits in a laptop Python process, and off you go. And almost all of our curriculum at the beginning of our data science program has this flavor. And this is a flavor inherited both, I would say, from computer science classes and from stats classes at Berkeley. And this is obviously the view reinforced by popular machine learning leaderboards, research, that you tend to get nice, clean data sets. And the interesting bits are the models, right? How does this model get tuned for this objective? So this is certainly important, but it definitely misses the big picture of what happens when you're doing data science in a domain. So data engineering is the sort of theme of the class we're teaching, and it includes activities like representing data, collecting it, organizing, assessing, moving. And I think primarily, mostly what you're doing is you're transforming the data from one format or one set of content to another format or another set of content. And that transformation of data becomes kind of thematic throughout the course. So some key characteristics is that we're dealing with large, evolving, diverse, messy sets of data. And I'll highlight, I think everybody remembers that data can be messy. They may not deal with it, but they sort of know in the back of their head that it's a problem. And maybe data could be large, but this idea that it's evolving over time, so that you actually don't have a data set, you have a feed, that some provider is giving you data over time. That provider may change the format or content of the way they're representing the data over time. You have to wrestle with that in an ongoing basis. Also that, of course, the data may be diverse. You may have many such feeds, and they are overlapping in their content, and you have to fit them together, integrate them. So that's all reality, and it leads to some thorny problems in how you do data transformation. The use cases are going to span teams in an organization. So issues of transparency and reproducibility, collaboration are very important. The objectives in data engineering and data science really are often ill-defined to begin with. There's a fair bit of data exploration that goes on, and of objective tuning. You think you're going to go do one thing with the data, you end up doing something a little bit different. And from a statistical methods point of view, that sounds rather suspect. But honestly, from a real world point of view, it's very, very common, both in the sciences and in application, that you start with an initial question, but it leads you to a whole set of other questions and purposes for the data that you didn't start with. So this idea of that sort of fixed data set, fixed objective is not very representative of really what most people are doing. And then finally, you do want a distillation to a repeatable, trustworthy process, because some set of the activities you do in data science is supposed to lead to something that is a reliable engineered artifact. And this is, after all, a course on data engineering. In this soup of goals, there are tools and models that mix across math, across software, across engineering practice. And the goals of the class are to get students to dip into all of this stuff. And more into software engineering practice, perhaps, than they've been doing in Data 8 and Data 100, which are the earlier data science courses. So, I've been running around saying this for like a decade, but it comes up again and again, so I don't have to quote myself. Data science projects largely focus on data engineering. Vicky Boykis is a well-known data scientist and consultant who, just in the community. And she once again, last year, 2 years ago, I guess, was on Twitter, and her methodology was a little more empirical than most, so good for her. Been curious about this for a while. I created a poll. As someone titled Data Scientist in 2019, I spend most of my time doing what? And she gave people choices. And what came out was pretty typical. Cleaning and moving data comes first. Analyzing and presenting data comes second. Picking features and models. So that's kind of what we tend to focus on in data science, a very distant third. And then deployment of those models in production, that last engineering bit, actually not that common with the title data scientist. And that you'd sort of expect. That might be a data engineering specific task. But look at how much of what is called data science is actually this data transformation and data movement. 10 years earlier, the tweet that I used to like to put in my slides was this one from Big Data Borat. In data science, 80% of time spent prepare data, 20% of time spent complain about need for prepared data, right? So this is like, one of those painful truisms of working with data. And these are two tweets separated by a decade, actually. So data engineering, it has roots and foundations. There's a long history of academic and industrial interplay, mostly in database research. That's sort of been the home for this kind of work in the ACM, if you will, over a long period of time. And I'm not equating data engineering with database systems research, but there is a ton of overlap, which means that because there was this interplay, there's a mixture of academic jargon, kind of mathy terms, big words that people don't understand, and industry buzzwords, which are also big words that people don't typically understand, just from a different lexicon. And so you need to kind of know some of both of those, and we try to make sure you do in the class. And that means it's also about formal foundations, which are nice when you have them, and best practices for doing things in the field, which are also nice when you have them, but may not be quite as mathematical. And you want to really learn from both of those. So we'll approach both. And then, I spent some time in the class, and here I'm stepping slightly back from role-playing a lecture. But I'll tell you, in the class, we talked in our first lecture about the fact that there's two general kind of approaches. You might think of these as two kinds of shops that you might end up getting hired into as a data engineer. They're sort of Java, Scala, big data shops, where everything they do is kind of using open source tools that are built around Java and JVM things. So think about Scala and Java code, as well as tools like Spark and Kafka and so on. So there's that kind of a shop. And the other kind of a shop is mostly SQL shop, where you try to get the data into a data warehouse in some form, even if it's in like a table with one column called stuff, that's just of typed text. But you try to get it into the database in some form, and then you're mostly doing your work in SQL. And I would say that, if you look at industry trends, the latter bullet, the SQL approach, is resurging and ascendant. So companies like Snowflake and cloud provider tools like BigQuery and Amazon Redshift have led to a real resurgence in the use of SQL. And also, as the data engineering field has matured, it's starting to look more and more like the traditional database management field. And having ad hoc Java and Scala code floating around is somewhat less of a best practice now, and somewhat more of a special case for very technical shops that need custom code. So the first bullet's a bit more Silicon Valley, but even in Silicon Valley, the second bullet is rising. It happens also at Berkeley that we teach data science in Python, and our students aren't that familiar with Java and Scala, and that SQL is a good complementary thing to learn. If you already know Python, you'll learn Java pretty easily, but getting really good at SQL is a new skill. And so we've decided to do our class on data engineering at Berkeley in SQL. But it's certainly not the only way to go. And we always are trying to point out places where, when we're using SQL, a similar thing would work in something like Spark, for example.
Joe, I have a question here.
Yeah.
Quick question. One of the programming assignments in my class involves feature engineering and model selection, so data transformations that they need to do on Spark. And we recommend Dataframes and Spark SQL API, so they can mix and match between the data flow abstractions and SQL strings. And I don't know how many students like to use it. The last time I ran this class, vast majority of the students used the function stitching Dataframe API. They didn't want to write SQL strings. Do you think this gap between these two worlds has largely been merged, or what do you see happening in the future? Do people fluently speak multiple languages, both SQL and these Pythonic stitching functions together, or do you think they're still largely separate?
I mean, I think the answer to that, Arun, and I'll speak in terms that will certainly resonate for you, but I'll try to make sure it resonates for the whole class. The distance between a data flow representation like Spark, where you're, or pandas for that matter, where you're kind of composing operators, and SQL is not a long distance. And that's in the original database papers by Ted Codd in the late 60s, that the relational calculus, a declarative language on which SQL was based, and the relational algebra, which is an operational language, very much like you see in pandas or Spark, are equivalent. And every database system compiles down from SQL to something that looks very much like pandas or Spark. So they're kind of dual, and it sort of doesn't matter which one you like better. So that's good. And tools today are recognizing that. What I will say is that in our experience, that facility with the SQL way of thinking complements very nicely what we teach in other classes. It gets you thinking a little bit higher level about what you want as your outcomes rather than how to get them. The other thing we do in our class is we spend a fair bit of time staring at the query plans that Postgres generates from SQL and thinking about them as data flows. So we are trying to bridge that gap, and I do think it's healthy to be able to do both.
Sounds great, thank you. And students, if you've taken DSC 100, you remember tuple relational calculus and relational algebra. Joey, this might be a fun tidbit for you. When I taught the 564 at Wisconsin, when I was in my final year of PhD, I polled my class. Almost half the class liked relational algebra better, half liked tuple relational calculus better.
See, yeah. I mean, relational calculus syntax is a little trying, and I tend not to teach it. But SQL is kind of trying. Pandas is super trying. So all these languages have their foibles. We'll get into this a little bit more actually as we go today. All right, so this is a little gray because I'm stepping out of role playing now entirely. This is a meta slide about our conversation I'm having with you folks. So today's kind of an example lecture. We're going to have 3 data models we're going to walk through, which is going to speak to this conversation we were just having. And then we can talk a little bit, and I've sort of got a choose your own adventure if we're short on time, about looking at transformations across models as a topic, or looking at how computer science tools can help us transform data engineering by using recent technologies to make things a lot easier. And we'll see how things go. Okay. Cool. So what you're about to see now, we'll step through is a sort of half a lecture or so topic from a few weeks ago in the class. So I wanted to start in our discussions by talking about data models and how we represent data. And I'm going to take 3 very common models that you may have seen, or you probably have seen, I hope, in your data science classes: relations, tensors, and data frames. And we're going to try to make sense of this. So this was born, this lecture, a bit out of an anecdote. I was a part of the team that put together our Data Science 100 class the first semester it was offered. It was 2 statisticians and 2 computer scientists. So it was a 4 faculty class to make sure that we kind of got a good mix of curriculum, and we started addressing some of the frictions across the fields and their viewpoints and integrating them. So it was an exercise in you be you, I'll be me, and let's see where that turns into trouble, and then we'll try to make sure that we integrate that healthy friction for the students. So I gave a lecture one day on, I think it was SQL, and one of the stats faculty, very esteemed person, came to me afterwards. So this is a senior faculty member in the stat department at Berkeley, and said, that was a very interesting lecture you gave. I'd never thought of it that way, because as you know, and this person looked at me with like raised eyebrows and said, I was trained in mathematics. With the implication that like computer science isn't mathematics, but isn't it interesting that we had something to say that she might find, pleasing or relevant or whatever. So I thought that was pretty funny. And what's clear is that obviously there's math foundations in computer science, particularly in data. Like I wish Victor Viano had been there to hear that comment. But what's going on is it's different math, right? Statisticians don't use the math that most computer scientists use, or at least classical computer science uses, which is more built out of logic. And so what we need to do here is we need to transform across our mathematical foundations, and I use that term actively because we're going to be doing data transformation. Right? But it is really important for you as a data engineer to understand these format translations that we're going to do, where you're like, I have a data file in one format, some person wants it in another format, what a pain in the butt. There's really actually some like mathematical foundations to this in these transformations, and you need to understand the representational power of these different formalisms, because that's why the tools that consume these different models are the way they are. So 3 very common models: matrices, relations, and data frames, right? And then the languages that sort of are natural to them. So with matrices, we have linear algebra, as you, I'm sure, know. With relational databases, we also have an algebra, the relational algebra, which you may know. I hope you know. It sounds like you do. And then with data frames, we have, I don't know, pandas or R. So data frames didn't have an algebra, although we've done work now at Berkeley to try to formalize them. And we had a paper in this past year that tries to capture as much of pandas as we can in a relatively clean algebra. So I'll allude to that briefly soon. And this picture is kind of the summary picture of how you might want to think about these data models. And I'm going to step out because this lecture's from a few weeks ago and I forget what slide is next. So let's just peek. Okay. So I am going to explain on this slide what these models are. So at a high level, without getting too formal, a matrix, something you're very familiar with, it has rows and it has columns and it has indexes for those rows and columns. So we have m rows and n columns. But the good stuff is the values, right? It's this array of values of shape mn, right? And all of those values are of a single type. So in the upper left, I've put a little orange box to say, that's the data type for the entire matrix. Okay. And it's important to note that this data type is going to have some specific properties in order for it to be a valid matrix, which we'll get into in the next slide. So it's not any old data type, right? It's the kind of data you put in a matrix, like numbers and stuff, right? So we'll formalize numbers and stuff in the slide. Any questions about matrices before I move on?
So Joe, we actually covered your distinctions between these three models in class. I think you tweeted about it, remember? So the students had a quiz question on this. What is the data model distinctions between these three?
Awesome. All right. So I'm going to fast forward through this part of the lecture. Did I give you these slides? That's great.
I think I took one of your blog posts, which has a diagram like this.
Okay. So this has been refined a little bit. So I'll breeze through, but I'll breeze through quickly. Relations, you've seen these before, right? You have a set of tuples instead of a ordered list, right? So there's no row axis, right? There's nothing on the left here because the tuples don't have an order. So you can't say which index of the set you're getting because sets don't have indexes, right? So you've n columns, you have m tuples, but they're just in a set. And then every tuple, of course, is a tuple, which is to say that it's a concatenation of values from a list of types. And those lists are named as in the domain relational calculus, I guess. I can't remember which one's which. But anyway, there's names and types for every column, as in SQL, right? Data frames try to bridge the gap. They say, okay, we're going to have row indexes 1 through m, and you'll be able to look things up by row number. We'll also have row names because why not? We have column names. Let's have row names, at least optionally. Seems like a handy thing to do, particularly if you want to transpose, right? You'd like your rows and your columns to kind of be symmetric. So we'll talk about this in a little bit. And they have an array of values, but like the relational model, those values are going to be typed by column, right? So it's not a matrix, the thing on the far left, because it doesn't have a single type for all the cells. It's more expressive. At the same time, there's a degenerate kind of data frame that is a matrix in which all the columns have the same type. So it has a compatibility with matrices, which is kind of what it was going for. Make sense? Should be familiar. Okay, briefly, let's talk about matrices. Critical thing about the matrix is that the data type that a matrix has to be a field in the algebraic sense, which means it's a data type with two operators, this operator, which we'll call plus, and this operator, which we'll call times. And they have to obey the usual laws of arithmetic, like commutativity, associativity, and importantly, distributivity of times over plus, right? The distributive law. You're familiar with this from elementary school. It's kind of in your bones. But if I tell you that you can have an array of Booleans, you might have to think a little bit. Well, what's plus for Booleans? Oh, it's or. And what's times for Booleans? Oh, it's and. And does that work? Does it fulfill all the rules? Convince yourself that it does. So that's, abstract algebra is like object-oriented programming. You have methods and then rules, but you don't actually know what the data really is. It's all sort of encapsulated. So if you're a computer person, you'll like abstract algebra. Anyway, it has to be a field to be a matrix. Otherwise, linear algebra doesn't work. All right, the sum and product and vector multiplication, all that for matrices won't make sense unless your data type is a field. All right, so matrices have to be on fields. In particular, you can't like put employee name into a matrix. It's not a matrix anymore. Now it's just an array of strings. Right? You can't do linear algebra on strings. So obviously the matrix might be full of values, but we allow matrices typically to have missing values, which are often in software represented as a NaN, which stands for not a number. But many tools and packages as inputs won't take a matrix with NaNs in it. So lots of times we have to replace our NaNs. We have to transform the data to get rid of the NaNs and give them a field value like 0, for example, or the minimum value or the maximum value, or whatever you choose to fill in for your NaNs. Okay. A matrix with lots of NaNs is said to be sparse. Otherwise, it's called dense. Okay, any questions? Okay. Tensors are a generalization of matrices to more dimensions, to have a bigger dimensional array. So on the sort of third from the left here, we've got a good old-fashioned matrix, m by n. That's a tensor of rank 2. If you go one to the right, to the farthest right picture here, that's a tensor of rank 3, which means it's got an array of 3 dimensions for its values, m by n by o, let's say. And so that's the only difference. It's still got to be a field and all that good stuff. Okay. We can also go in the other direction. A tensor of rank 1 is called a vector. You're familiar with that. A tensor of rank 0 is just a value from the field. Single value. It's called a scalar. Okay. And dense matrices are very standard in like scientific computing, particularly in simulation. So imagine simulating the weather. You model the sky as a 3-dimensional point cloud. And then you say at every point in this space, which way is the wind blowing, for example? What's the direction and what's the velocity of the wind? Yeah. So obviously it's dense because the world doesn't have holes in it, right? So if you're doing a simulation, it's a dense simulation. In machine learning, it's also very common to create dense matrices. You see this, for example, in deep learning very naturally. Okay, so very important model. Now the relational model, I won't spend as much time on because there's nothing more to say about it than you probably know. It's got a schema. It also has at any given time an instance. That's the rows that are in the table right now is the instance of the relation. So if you think about this in a practical database, it's the data currently in the table is called the instance. We can have missing values in relations as well. They're typically called null, and they're interpreted to mean I don't know what should be there, as opposed to missing. So missing data in a relational table just isn't in the table at all, because there's no notion of density here. There's just rows. If there's a row in the table, it's there for a reason. If there was nothing to write down, you wouldn't have had a row in the table. Okay, so nulls are values that somehow there's a particular aspect of that row or attribute of that row that I don't know the value for. This is a somewhat slightly different interpretation than nan, which is typically representing missing. All right. Optionally, obviously, we can have keys for relations, and the keys can be a list of columns, so composite keys. And keys allow us to index into the relation, right? They allow us to identify a unique row or tuple. In the absence of keys, we have a multi-set instead of a set of rows. And I'm sure you've talked about this in SQL. So you can have duplicate rows, and the number of duplicates matters. Okay. But if you don't want to have multi-sets, then just make sure you always have a key on every table, and then you just have set. Okay, so let's talk about mapping tensors to relations. We can think of a tensor as a relation, and really just the relation is the sparse representation of the tensor. Instead of the picture on the left, where we have our 4 numbers arranged in a spatial grid, that spatial grid, by the way, is just a data visualization, right? That picture on the left, that blue square with numbers in it, that's a picture. It's not a mathematical object, right? The mathematical object is an abstraction. The picture on the right is the same mathematical object, but it's being modeled as a relation and visualized differently. And what we've done is we've said, let's lay this out so that the row ID and column ID are explicitly written down on the right-hand side. So row ID 0, column ID 0, value 12.2. Same information laid out differently. Notice how the nan on the left is not stored on the right. So it's a sparse representation on the right. Now, it may not be a smaller representation depending on how many nans you have. It's just called sparse. It's just a term. Also note the schema on the right. We've got an ordinal, which is a numeric value that starts at 0. Actually, really, ordinals typically start at 1, so I'm cheating a little bit by 0 indexing, but it's an ordered index number. We have a row ID, a column ID, and then the value has to be in your field type, whatever that is. Maybe it's floating point numbers. Okay. Questions on this mapping? It's pretty straightforward.
So again, I had an extra credit question in my quiz where I asked them to compute a Gramian matrix in SQL. Great. So some of them are familiar with it. I think a quarter of the class got it right. So this is great. Good to see this.
Excellent. How about the other direction, folks? This is where it gets thornier. We have lots of relations in the world. They tend to be sparse. They tend to have lots of rows that could possibly be there, but aren't. So think about a table of people. last name, comma, first name. There's lots of pairings of last name and first name that you might not store. It's not really helpful to say, Joseph Kumar is not in the database, or Arun Hellerstein is not in the database. It's like not interesting. Why write it down, right? So sparse representations are very common in relational data because all combinations are not interesting anyway. Relations, however, cannot always be expressed as tensors of any kind, sparse or dense representation, for two reasons. One, we may not have axes in our relation, particularly because many of our columns have no interesting order whatsoever. It's all categorical data, if you're familiar with that term. That was something we would have taught in my class prior to this. So you can have a database of, teachers. That's last name, first name, social security number, hair color. None of those attributes could be a dimension because none of those attributes have an intrinsic order. Sure, you could order them like alphabetically, but it wouldn't give you anything meaningful. You don't want to take you wouldn't want to smooth the data across the order of hair color because it wouldn't teach you anything, right? If you decided hair color is ordered alphabetically, there's no proximity there that means anything. Okay, so you don't always have a meaningful order on your types and relations, and you may not have a field value to make it be a cell either. So there are going to be columns that can't be an axis, like last name. That also can't be the value in the cell because they're not fields. They don't have plus and times that follow the rules. All right, so not all relations can be losslessly encoded as tensors. Keep that in mind. You're going to lose information if you want to coerce your relation into a tensor. So suppose you're using TensorFlow, man, and you want a tensor. What are you going to do? Well, you're going to have to pick some columns to be your dimensions. So you're going to have to choose an order on some subset of the columns. And then whatever column you wanted to put in the values, you're going to have to coerce it to a field. By the way, it'll be a sparse tensor maybe, and that's maybe fine. All right, so that's not sort of our issue. But basically, when you're converting a non-field value into a field value, that's an example of featureization. So I have a little SQL example here in the bottom right corner from the IMDb movies database that Aditya likes to use. This is all the databases of movies on the IMDb website. And we've made ourselves a tensor, or rather we've made ourselves a numeric relation, which we could turn into a tensor, where we've taken the name of the movie, the title, and we've replaced it with its length. Okay, title len. So it's a featureization. It's a dumb feature of a movie title, but it's a perfectly reasonable feature. It might be one of many useful features. All right, and now we have a thing that could be turned into a tensor. We could say title led by production year, and then we could count the number of matches. So we could say, hey, in 2005, there were 17 movies whose title had only 2 letters in it. And we could look over time at the trend of small length movie titles over time. And I bet you it's increasing. I bet you in the early days of Hollywood, very few movies had titles that were as short as 2 letters. So is that interesting? I don't know. Maybe for you it's interesting, right? But the point is that when you coerce categorical data into numeric data, there may be things that are interesting, but you are losing information. I cannot recover from this table that I see in the bottom right. I can't recover the original data. The titles are gone, right? Once we put this into a tensor, we've lost information. Questions?
Audience, any questions from the students? Feel free to raise your hand. Okay, so far so good.
So far so good. And note that throwing away data, so to speak, is not necessarily bad because in some sense you're smoothing, right? And sometimes the data is like too specific and you want to smooth, and title lengths are a great example. Like there's something interesting about titles where I don't need all the bits about which letters are in it. I just want to know how long it is. It gives me an interesting smooth feature to study. Okay. All right, let's talk about data frames. It's this mix of ideas from relations and matrices. Historically, by the way, data frames were defined for the language S, which is the commercial precursor to the open source R language. Okay, so if you wonder where the heck did data frames come from, they came from the statisticians who designed S. So it was an effort to have a sort of familiar matrix-like data structure, but one that could really handle tabular relational data. So as you know, it's ordered, it's got named rows and columns. Only columns have types. Now beware that there isn't a standard definition of data frame. So the one I'm presenting is mostly the R and Pandas definition of a data frame, which are pretty similar. But some people will define data frames as, you know what, they're just basically relations with maybe an ordering key for the columns so that we can have column order. I'm sorry, for the rows, excuse me, ordering key for the rows so we can have a row order. All right, and if you believe those people, so most of the Spark-based data frame libraries like koalas are just that. They're really relations. They might offer you a way to order the rows. One of the things you'll be able to tell a signature that they're sort of more relations than data frames is they don't have transpose. That is to say, the rows and the columns are fixed. You really can't turn columns into rows and rows into columns. But we're going to try to be expansive and go with the R and Pandas style. And there's a link here in the slides, which I'll share with Arun. We had a paper last year at VLDB where we formalized both the data model, which is something I sat down and did one night at my in-laws' house. So I have a very specific visual memory. And then formalized an algebra over that data model. So it's basically this picture above. But we get down to the Greek letters and definitions. And here's the thing about data frames is they're trying to be symmetric like a matrix. This is one of the goals. So matrices are fully symmetric. You can transpose rows and columns. No information is lost, right? And it's really just a matter of perspective. And that's what lets us do, nice linear algebra equations, right? Because sometimes you need things arranged in different orders depending on where they appear in your linear algebra expression. Relations are for sure not symmetric. There is no transpose on relations. What the heck would a transpose of a relation do? Let's just ask ourselves that question. What is the if we did a transpose of a table, what would, the first row would become the first column, okay? What's the type of that first column? When it was a row, it had a bunch of types. It had n types all lined up. When you flip it to a column, it's just kind of a soup, right? It's got n different types mixed together in a single column. Relations don't like that. Okay. And in fact, if you're a purist, it's not possible, right? You can't put an integer and a string into the same column. Can't be done. It's illegal. So data frames are going to try to walk a middle ground. And the way they're going to do it, and this is critical, and it's kind of hidden, data frames don't tend to talk about this, is that we're going to have an operator which does type induction. It takes a set of values and it guesses or it chooses a type for that set of values. So think of taking an array row and then assigning a type to the values across that row. More importantly, when we do the transpose, it becomes a column. Now we have a column, we have to assign it a type. So let's do that with induction. And we're doing it, importantly, on the instance. We're doing it on the data that we have today. So when you do transpose in Pandas, let's say, it's going to look at the data in your data frame and choose the column types after the transpose. Now, if you take that same Panda script and you apply it to a different set of data, it might actually choose different column types the next time around, silently, without telling you. So if you're in a repeatable process kind of system, like a database where there's updates going on all the time, that's a nightmare, because that means your column types are changing on the fly as people are inserting and deleting rows. That's a horror show, right? But for exploratory data science, it's great.
So, Joe, I have a question.
Yeah.
In the SQL land, they have pivots and complex table pivots and stuff. That's not from the relational model. That's from the SQL world, where they added a lot more procedural and other support. People in the BI world use pivots, right? And what's the relationship there with data frames? Do you think they were kind of inspired by similar business needs to pivot stuff?
So do you guys cover pivots have you done that yet in class?
In SQL? No, I think these students have taken only the introductory database class. We have an advanced class where we cover that as an elective. So
student Arun, that's a great question. And I'll ask you to hold your questions on that till later in lecture.
Okay, sounds good.
Wasn't sure quite what role modeling we were doing here. I will not treat you as Professor Kumar.
Okay, we have a question from a student. Andrew, you have a hand raised. Feel free to unmute and speak.
Testing. Okay. So when are transposes used? I don't think I've ever used one over the past few years, so I'm curious.
I'm sorry, can you ask the question again? I think I just didn't hear it.
So when are transposes used in practice?
I mean, in matrix, in linear algebra, you'll say like A times A transpose. Happens all the time.
But what about in the context of data frames?
Well, if your data frame is a matrix, you will absolutely do that. So you might, oftentimes what you do in data frames is you take your data and then you coerce it using data frames into matrices, and then you do linear algebra. Like, that's pretty common. So the simplest answer I can give you is if your data frame is in fact a matrix, which is to say all the columns have the same type, you might directly just transpose it for purposes of doing a matrix transpose.
And
Having said that, it's quite common that somebody will give you a table and you're like, it's years by months, and I really want it to be months by years so I can join it with this other thing.
And one other thing I would add to that, Andrew, is transposes can often happen implicitly in many linear algebra procedures and machine learning procedures. Like, cross products are very common. Riemann matrices are very common for things like OLS, for PCA, SVD, all of these things. So implicitly, the programming language implementation needs to support transposes. Oh, we have another question from Yoav. Yes, Yoav, go for it.
Yes, hi. So this inference of the type of the columns that you do after you transpose, what if it doesn't work? I mean, basically, what if you have a bunch of different types?
I'm going to ask you to hold your question as I asked student Arun to hold his question. We're going to see this in just a bit. You know, I can't give you a very principled answer, so we're going to see what Pandas does.
Okay.
It has to do something, right?
We have one last question from Siddharth, and then we can move on, Joe.
Okay.
It wasn't really a question. It was kind of like a follow-up from Andrew when he was asking about the question of transpose in the context of data frames, pure data frames, not matrices. Would one-hot encoding be considered a kind of transpose?
One-hot encoding, did you say?
Yeah.
Yeah, so one-hot encoding is actually a lossless featureization if you do it really one-hot, right? So you basically take every possible value, gets its own column, turns it into a Boolean field value, right? And now you have a tensor, and you haven't lost any information. So that is a form of coercion, type coercion to a field, namely the Boolean field, and it's lossless with a caveat. What's the caveat? Anybody know?
It summarizes, maybe?
It doesn't actually. It keeps
Oh,
all.
it doesn't summarize. No, yeah.
Yeah. What's the potential? Why am I saying there's a caveat?
I guess a huge amount of actually, yeah, it desummarizes, so it's a lot more data which gets created.
Well, it creates a very sparse matrix, right? Lots of
Yeah,
zeros.
but it'll still take more space, I would guess.
Could be, but let's for a moment set aside representational costs. There's a expressive limitation, a semantic limitation. Any thoughts?
I think one-hot encoding can lose information from the string domain, like ordering, other properties of the strings, and so on. It's treating it as a set. There is information in the string too.
Okay, so let's we have to be a little careful how we're using one-hot encoding. So if we take every distinct value in a column, we treat it as categorical, and we do one-hot encoding on that domain of the column of all the distinct values, it's lossless.
It's lossless in the set interpretation of that column. But if you treat the strings as meaningful things, like CA versus California, then one-hot encoding won't be able to distinguish CA versus California as duplicates, right?
Indeed, and I think from a type theoretic perspective, again, it's lossless. So we had a column that was of type text. It had CA and California in it. Those are different. And moreover, in a data frame model, when we have the CA bit column and the California bit column, we've preserved the strings in the names of the data frame columns. Now in the matrix, they're gone.
Yes.
So doing the linear algebra, we've lost those names entirely. But the data frames actually got the information. So this is a little pedantic, but what I was actually going for is related, which is one-hot encoding creates dimensions, right? Columns based on the data you have right now. And if you don't have all the possible category labels in your data set, your one-hot encoding will not work on the next data set you run your script on. And particularly if you one-hot encode a set of data and I one-hot encode a set of data, and we don't have all of the same labels, our data won't line up. And that can be tricky if you've lost your column names. Okay, so that's what I was looking for, is like one-hot encoding has a, like any pivoting operator, it only gives you column names for the data you have today. So it's a function of the instance, very much like we say at the bottom of the slide. Great questions. I would like to move ahead if we can. Everybody,
Continue.
has anyone, any questions of clarification? Is anyone confused at this stage? And Yuval and Arun, you both have questions, you know, that I'm going to try not to lose track of, but if I don't answer them over time, please ask again.
I'll remember and ask again.
Yuval, I think we're going to get to yours right now.
Yes.
Okay, you asked about pivots. So here's the thing, types, you know, they're critical, they determine meaning. This whole little quibble I just had with Arun was about, you know, if I have a column of states and I write the string California and I write the 2-letter string CA, those are the same state. And if I had a data type state, they really should be the same object, right? But if I have a data type text, they're different objects explicitly. And so the type you choose for your column determines the meaning in a very real way. Like it determines what are distinct values and what are the same, right? So if we have a column called, I don't know, organism, all people might map to the same organism, and then people are all the same, right? And for some applications, like, I don't know, population counts, that's great. But for other applications like teaching methodology, it's not so good to say all people are the same, right? So types really determine meaning, and they're very dependent on your goals of your analysis. Hence the discussion about population statistics versus educational statistics, right? You have to decide these types, they make all the difference in your interpretation of the data. So let's see what Pandas does with this little data frame I have here. Name, day, score. It says name is of type object. So I think that answers your question, Yuval. In Pandas, if we don't know a type, we go to the root type of the hierarchy. We just say, it's an opaque object. I can't unpack it for you, but it has distinctness to it. So every distinct bit string is different in that type. And that's the only thing we can do is compare the bit string. Make sense? So there's a default type induction, which is object.
Yoav, do we have a follow-up question?
Yeah, sorry. First, the name is Yoav, not Yuval. But
Sorry, Yoav.
Yeah, no, my question is, what happens if, let's say, you transpose this matrix, and now you have a whole mix of types? Then what does it do?
Wonderful. Hold your question just a tiny bit longer, Yoav. You're now like 2 animations ahead of me. Let's transpose it. You're 1 animation ahead of me. All right, this is a perfectly reasonable matrix. Now what are the types? It says Pandas. They're all object, which makes sense. What else is it going to say? It could say that they're text, and then we could do textual things on it. And I think, you know, casting object to text is probably lossless in Python, with the following exception I was taught, which I didn't actually realize when I made these slides. When it says object, Pandas is actually remembering cell by cell what type it induced for that cell. So it actually is keeping track of the lineage of these types, which you'd think it would be smart about. But watch the next, which is, I'm sure you'll have your next question. What if I transpose back? Look what happened. It did type induction all over again, because that's what Pandas does. And in doing its type induction, look what it came up with for score. It said score, yeah, I don't know what scores are. But originally score was in int64. I don't know why Pandas did such a bad job here, but more generally, I see this a bunch. That transpose is not, it's not its own inverse in Pandas, in data frames in general. Because type induction is this black box, and it's like a classification algorithm. It's heuristic. So data frames, like, they're kind of messy mathematically. We can't say that transpose is its own inverse, for example. This just comes up a lot, unfortunately. Did that flush it through your option?
Yeah, pretty much. I mean, I'm aware of this mostly because, you know, usually when I build data frames, I give it a dictionary of lists. And And then each list, I have to be careful, is one type. So yeah. So I always thought that that's the only stage it's done. But you're saying it's also done when you're trying to do it when you transpose.
Yeah. Now you could choose to build a data frame library that tries to preserve these properties that you like mathematically, but it would have to make some hard compromises. It's not clear to me actually even what that would mean. So no one's thought very hard, honestly, about how type induction fits into the algebra of data frames. It's just been this like hidden feature that's in the background, but it's first class in the model, really it is. So that was part of the contribution of that formalism that we had in that paper, was to pull this out and get us all to stare at it.
Okay, thank you.
Sure. And this is a class, right? So this is not supposed to be a research talk. So I'm sorry if that came a little slow, but I wanted to make sure students, when we're teaching this at Berkeley, are getting this point, undergraduates in data science. How are we doing on time? We're at about 12, and we go to 12:20. Is that right, Aaron?
Yes, we have the slot till 12:20. So how much more do you have, Joe? How many more?
Is that my last slide? Let's see. We're getting close. I think this is my last slide, and then I was going to go into one of these two sort of interactive demos, lectures.
Yeah, feel free to continue.
All right, so let me close out my discussion of data frames by saying the R community, and I give them a fair bit of credit for doing this because Pandas hasn't gotten there yet, that community. The R community has leadership from this guy, Hadley Wickham, who's a statistician. I can't remember where he was at Rice for a while. I think he might still be there. To define what's called tidy data. And he has a set of software called the tidyverse for R. And tidy data espouses what's he calls the tidy data model, which is that every variable should be a column in your data frame. So variable, think of that in the statistical sense, everything that can change across observations. Every observation should be a row. So he's saying, here's the way rows and columns should be chosen. Rows should be observations, columns should be variables, and each type of observational unit forms therefore a table. This is the relational model of data. Okay, so he's found, he's landed on a representation that is good called tidy data that is indeed relations. And he's saying the desired format of a data frame is a relation. So that's nice. It leads to some kind of syntax or nomenclature confusion because he says things and then in parentheses he says in databases this is referred to as, and he's introduced his own nomenclature, but be that as it may. So to sort of live with tidy data, the discipline is that you want to wrangle your data into a good shape. And the reason we allow data frames to have non-tidy data is for the transient wrangling from one form to another. You give me messy, horrible data, I need to put it in the computer somehow, and I need some operators to work on it so that I can turn it into a nice, tidy set of data, right? And so very often the reason for data frames is to deal with data transformation and to wrangle messy data into either a matrix or a relation, or to wrangle from a relation to a matrix and back so that I can move my analysis tools from, say, linear algebra tools to relational algebra tools for different tasks. So I would say data frames are best thought of as this kind of model for translation or for data in transition, model for transformation, I should say. And usually at the end, you want either a tidy data frame, namely a relation, or a dense matrix. Good? All right, with that, we'll stop the PowerPoint phase. We had two topics to choose from next. And I think Arun had asked me to spend time showing you some of the research that led to Trifacta, which is now a company that we started, and it's the provider of Google Cloud Data Prep. So it's sort of becoming a bit of a de facto industry tool for data transformation. All right, so I think we're going to do number one instead of number two. If you're curious, sometime I can share with you the Jupyter notebooks for number two as well. All right, everybody take a stretch. We got 20 more minutes of this nonsense, so.
Sounds great. Thank you, Joe. So audience, any further questions at this point? So Joe, you're okay with this demo being recorded as well, right? As part of the talk?
Sure, absolutely, yeah.
Okay, great.
Not a problem.
Great, looking forward to it.
Okay, so folks, sorry to keep you from your lunch. I will try to keep this lively. We're gonna shift screen share here to a web browser.
While you're doing it, Joe, we have a question from Siddharth. Yes, Siddharth, go for it.
I guess question in like do you know like in industry say how many people would be working on this kind of data transformation or pipeline at a time?
Yeah,
How would you coordinate it? Sometimes it could be sequential. You have to do one step first before going to the next.
absolutely. So it's hard to answer that directly. One answer is you can look at job ads for data engineer versus data scientist. And all the articles this year in the trade press are about how there are more calls for data engineers than data scientists, and it's the faster growing profession. So that is what it is. You can take that for what it's worth. There's a lot of noise in the roles that go under those labels. And when you go talk to people with the title data scientist, you get this kind of Vicky Boykus answer, which is actually, mostly I'm a data engineer. That's most of my day. But I have a degree in statistics and I was hired to do data science originally. I just had to skill up on all this stuff because this is actually what matters. So I would say in practice, what people are reporting is like what Vicky Boykus reported. People are spending, 60% of the time, 70% of the time in these projects on issues that are more like data engineering than data science. The roles and responsibilities for who does that varies across the way you run your shop. So in some shops, these are segmented roles. The data engineers prepare the data and then they put it in a reference format and the data scientists are stuck with that format and they're not very good at transforming. And if they want transformation, they have to go talk to a data engineer to help them because they're just mere statisticians. And in other shops, it's much more fluidly skilled. In many shops, the data scientist lives in a application domain, like you might be in the fraud department of a bank. And you know what? The fraud department might do everything. It's because those data scientists just are on their own and they take care of their own data. They do all the engineering, all the data science and everything. So it really varies quite a lot.
Okay, got it. Thank you.
So Joe, one quick note on that. So Yoao, who you just interacted with, I don't know if you saw the participants list. He's one of our ML faculty, and he and Alan were involved with the Master of Advanced Science, the data engineering degree that Alan mentioned. And HDSI is also very interested in this space. We are thinking of launching new courses and hiring more folks that are data engineering for data science and systems and stuff like that. There's also an online master's coming along where we are still thinking of drafting a course. So your course is very timely. It'll help us think more about this along these lines.
Great. It'd be awesome to see the diversity too of kind of what you folks come up with and compare notes. It'd be very
So I
cool.
have one last question before we move to Trifactor demo. Honestly, for small data, even as a database person, as an ML systems person, whatever, I've worked on this area for so long. I absolutely love spreadsheets for small data. One reason is the direct editability is just so much more convenient. Relations and matrices and data frames, all of them are not good enough for me for direct editability. What is your take on that? Trifactor clearly took a route where you blended something of that sort, right?
Mm-hmm.
What's your take on that?
So at the expense of actually seeing the tool, I will answer, but I will answer briefly so that we can have context for everyone else. There are good things and bad things about spreadsheets. And by the way, Aditya does research on spreadsheets. So he's got lots of opinions. One of the good things is direct manipulation and visibility into the data. So the spreadsheet has a built-in visualization, which is a grid of numbers and characters, right? A table is a visualization, a table in the sense of like a spreadsheet grid. And it's extremely useful, particularly with small data, to look at your data, right? And I'm a huge proponent of the idea that you should look at your data at every step, whatever you're doing anything. Pandas should by default show you a table at every step and draw charts for you. And Trifactor does that. And I think so much is unlocked by keeping that intuition going as you go step by step through a data science pipeline. And spreadsheets do that, and it's wonderful. Spreadsheets have all sorts of foibles though. One of them is they allow you to update the data in place, and there's no data lineage. So if you go in your spreadsheet, you're like, I'm going to replace all the values less than epsilon with 0. And then you give it to your friend. They have no idea that happened. And there's no way for you to remember tomorrow that you did that. That's terrible. And one of the reasons people buy Trifactor or switch to it is because someone's come in and audited them and their people were using spreadsheets and could not answer to the question of where did you get these numbers. So that's the biggest complaint about spreadsheets, is that they're not programmatic. They don't keep track of updates. And then the other one is that the cell-based formula model, where each cell can be a different formula, is quite complex and doesn't scale nicely. It's really handy, but column-based formulas are a lot more tractable. So those are two beefs with spreadsheets. Anyway, let's move on. But I think your reason for using them, which is get your eyeballs on the data, is primary. That's like super important and wildly undervalued in our data science curriculum. Wildly undervalued. We're teaching people Python rather than having them look at data because spreadsheets are for accountants and they're dumb. I just don't understand that outlook. It's terrible. So I have a few comments on that at the end if we have time. All right, editorial off. Let's jump very quickly into a Jupyter notebook. Another nice Berkeley product. My friend Fernando Perez in the staff department who led the development of Jupyter is a super influential guy. So what this lecture is we go through and talk about what I call data unboxing first. If I give you a data set, what the heck is in it? Super valuable skill. We tell you, don't forget, which we taught in Data 100, to use your basic Unix tools, or if you like, your graphical interface in your operating system like Windows or Mac to find the size of the file, show me the first few bytes of the file so I can just see what's in there, and use your eyes. Because the first time you see a data set, how are you going to get intuition? Without some intuition, life is hopeless. Now, you can have computer assisted intuition, which this doesn't do, and I'll talk about that in a minute. So you can use algorithms and code to produce something better than the bytes. But even that, you're going to want to eyeball that and say, oh, what did these algorithms output? Maybe they'll tell me something about what's in this data. And then we talk about what to look for in the data and how to classify your data into different formats. And I'm going to skip this right now. I even mentioned EBCDIC and ASCII for those who know what that is. And we go through some examples. So, briefly, here's some data in my file system with its size. And then we look at the first few bytes of one of them. I have the students talk about that. We look at the first few bytes of another, have them talk about that. And then we shift to where I'm going to jump in the middle of this lecture and talk about low-code interaction in Trifacta. So given everything we've seen, the next step to clean up data could be to stay in our sort of Data Science 100 Jupyter notebook using pandas and your favorite plotting package to write code for visualizations. But what that means is that every time you do a line of pandas, you're gonna have to write a matplotlib script underneath it to plot the data. And people don't do that because it's a pain in the butt, because you're asking people to program visualizations all day long. It's not a really pleasant interaction. It's very time consuming. So instead, we could try a purpose-built visual data preparation tool. We'll look at Trifacta. Editorial comes out of research that I've been doing over many, many years. And since it's a Berkeley class, I pound my chest and say it's good Berkeley stuff. Ordinarily, people interact with Trifacta via a web UI. We're going to do it via a Python library from our notebook. This Python library actually is not yet publicly available. I wrote it, but it will be available shortly. Real engineers are cleaning up the code. So we'll do this. To do this, we import Trifacta as TF, and we give it a, interesting. We give it a file to Wrangle, all right, which is this text file. And it's going to upload that file. Oh boy. Live demo. If it doesn't break, it's not a live demo. I'm not in the right directory, or I've moved the data. Embarrassing. All right, give me a sec. I need to reset.
Yes, during that we have Phil also join us. Phil, go. Hey, Phil, thanks for joining.
I think I need to move to just a different example of the notebook, the live example from class. Sorry, I'm a little distracted. We'll relaunch Jupyter. Great. Sorry, folks. Zoom. Share screen. All right, same notebook, different directory. Now let's just make sure our data is here. Hooray, it's here. Okay. So going back into projection mode, we import our libraries, and we now going to upload this file to Trifacta in the cloud, and it's not going to fail because the file exists this time. In a minute or so, we'll have an object back called JC1. JC1 is a Python object that contains a connection state to the Trifacta cloud service, and we'll be able to use it to manipulate Trifacta essentially on this file. So the file is uploaded. Now we can open JC1. And what this is going to do is just pop up a new tab with Trifacta's web UI. There's other things we can do like profile the data in the notebook and stuff, but we're just going to jump into the fully immersive visual interaction from Trifacta. So it's taking that raw data set that we had looked at very quickly along the way, and it's bringing it into Trifacta. And so at this point, while it's loading up, I'd like to encourage folks to raise your hand and tell me, what do you see here that you didn't see in a text dump of the first number of bytes of this file?
Students, raise your hand, participate, or type it in chat. So Andrew says histogram, predicted type.
Excellent. Those are two great things to see in this file. So histograms and predicted types. Note the histograms. This is actually a little bit of a different kind of bar chart than this one. So they're not all histograms, it turns out, but they are all bar charts. What's going on in this column versus in this column in the bar chart? There's a big hint to the column names. This, by the way, is real data from Jeopardy, from the Jeopardy website, or the Jeopardy fan website.
Andrew says category sorted by count, others are sorted by value.
That's correct, right? So the type of visualization we're giving depends on the data type, it turns out. They're all bar charts. Bar charts are incredibly useful univariate representations, but for categorical data, we want them ordered by frequency. And for ordinal data, for data that has some ordering, like dates, we want them ordered by the ordering implicit in the data type, and then it's a histogram, right? So great. So knowing the types, doing the type induction allows you to do type-specific data visualizations that are handy. And you could imagine doing, like, inferring a geotype and showing a map. You could imagine inferring a text type and showing a word cloud if you really wanted to. Word clouds aren't very useful, so we don't. But you know, types and visualizations go together. Now, one thing you're not seeing in this data is sparsity, because there isn't any, but there's indicators of sparsity and other things that we'll see soon. All right. And, you know, here's an annoying thing. What's going on in this column? Any observation? Okay, well, first of all, we actually do have some sparsity, so that's nice. So we're getting that information as well. That's handy. What else is what's funky about this column? What might I prefer?
Seem to be a lot of outliers.
All right, there are a lot of outliers. What do you notice about this column? Nobody?
And Andrew on the chat says it's detected a string. Siddharth says it should be ordered in the dollar amount, but it is not.
Thank you. Yeah, money, like the amount of it kind of tends to matter to people. Or if I give you a paycheck, I say, you have a unique value for your salary. You don't need to know whether it's bigger than mine or not. It's just, it's unique. That's not helpful, right? Money's a measure. So this interpreted this as a string. I don't like it to be a string. Why did it interpret it as a string? Well, I don't know, it's got dollar signs and commas and all kinds of stuff, right? Very annoying. So this dollar sign thing bugs me. So I highlighted it. And guess what? I said, hey, are you trying to get rid of dollar signs? Because if you did, this would be your histogram. Awesome, right? Let's do it. Oh, look, I changed my data, but I got a recipe over here, unlike a spreadsheet. It says, here's what I'm doing to your data. I was hiding this, but now I'll show it to you. The first thing I did is I broke it into rows with \n, and then I split it into 7 columns, and then I deleted a column, and I replaced these dollar sign with null. But we still got, now we got a thing here that we have mismatched values. So everything, it turns out, in Trifacta you can click on pretty much. And we use a model called predictive interaction, which says if you clicked on something, it means you probably want to do something. So let's take your interactions and use them not as a command, but rather as a feature from which we can predict what you might want to use as a command. Okay, so we call it predictive interaction. So when you click on the feature missing values, we highlight the rows that don't match the data type. and we give you a ranked list of suggestions. And for each suggestion, we offer you a preview of what would happen if you took the suggestion. We also offer you a sort of high-level Englishy looking summary of the code that we're proposing, so that if, for instance, you don't like it, we'll see you can go in and edit it. So in this case, I don't want to delete the rows that are mismatched, and I don't want to keep only the rows that are mismatched, and I really don't want an indicator column that says they're mismatched. I want to change them so that I don't want any of these actually, do I? I want to get rid of those darn commas, okay? So let's try the trick we did before. We'll give it a different feature. We'll just highlight a comma, see how it does now. Now it says, oh, it's comma separated data. Don't you want to split it? That's not what I want to do. It says, oh, are you interested in pulling out the commas? No, that's not what I want to do. But if I scroll down, I want to replace delimiters with space, I mean with null. That is what I want to do. So I'll choose that. It gives me a preview to make sure it's right. That is my numeric value column now, okay? So this is one of the innovations here, predictive interaction. It says, get your eyeballs on the data, start to point at features in the data, whether they're examples in the data cells or whether they're overall trends in the bar charts. Use those to guide people through very simple, sort of almost Google search-like ranked lists of things you might want. And then importantly, for each of those, provide again a visual preview of what they would get if they chose that step. Because without that visualization, it's really hard to look at one of these lists. I don't know, let's highlight backslash, right? We'll get a bunch of examples. I don't want to try to figure out what all these commands mean. If they were in pandas, it'd be a horror show. At least I sort of made them Englishy, okay? What I want is I want to look at the data, right? This is wrong, this is wrong. That's kind of interesting. How many backslashes do you have, right? So this deep interaction of kind of inference to guide you through the task, and then program synthesis, which is the generation of program code from from a vague specification. That's the field of program synthesis in computer science. Seen a lot of work in the last decade, coupled with visualization of outputs. So we call this the guide decide loop. The software, you guide the software to features that interest you. The software guides you to choices, and then you decide what you want. Having said all that, at the end of the day, we have a recipe, and you might need to edit code. And for each command in here, you can go in, you can say edit, and you can go through typically a wizard, okay, to edit the code. And you can do that interactively. So if I start pulling out strings here, if I don't like any of the suggestions, that's fine. I can just go to the recipe editor and start picking formulas the way you would in Excel. And other things that'll happen here are you can step through the code and see how it changes your data very quickly. So visualization in time of your scripts to do kind of visual data lineage. If you want, you can look at the actual code. And we have our own data wrangling language that's not pandas or R, it's Wrangle. But if you want, you can actually get in here, and there's a fully specified language, which we typically don't want to look at because it's too hard to quickly parse. What you really want here is you want something that you can eyeball quickly. What is the script doing more or less? If you want the details, you can get the details. So there's a ton more in the tool. There's things like programming by example, which you may be familiar with Flashbill. There's a thing that'll recommend pivots for you or unpivots. So pivoting and unpivoting are first-class operators. It deals with nested JSON data. It's got lots of sort of features that'll help you try to figure out if you have two data sets, what to join them on, or if you have n data sets that have different schemas, how to union them together. And it does this by doing inference on things like the metadata, the values in the data, right, and their distributions, models that we've built in the past based on other people's data, and so on. Bottom line, tools like this, and I'll wrap up here, are really useful for two reasons. One, non-experts can now do these tasks. So you don't have to learn pandas to be able to do data transformation. Pandas is very technical. It's got 200+ API calls that are available to you. It's very high learning curve. The second reason this is useful is experienced data scientists should not be sitting in a text editor writing code. They should be looking at data. So this is getting your eyeballs, your focus on actually the content of what you're working with, distributionally as well as with examples, every step of your data transformation. And I feel that this is highly undervalued in the way we teach data science. Hello, Phil. That was the Phil you were referring to. It's nice to see you. Phil was involved in some of the early research on this project. Phil Guo, nice to see you. All right, I'm going to wrap up because you guys need to go. Actually, you know what? Let's do this. It's 12:20. You got a flavor of my class. Maybe what we should do is ring the bell and let people leave. And if folks want to stick around and chat for a little bit, I can stick around too. Does that make sense, Arun?
That sounds great. So thank you everyone for joining, and folks who can stay back, feel free to stay back. We'll chat for maybe 10 minutes, and then Joe also has to go for lunch, I guess. Thank you again, Joe, for visiting us for the great talk. We went all the way from very abstract math to a very concrete tool demo, so that's spectacular. So the trifactor tool itself is pretty awesome. I remember reading the predictive interaction paper when I was in grad school with you and Sean and Jeff and others. So it's great to see how far trifactor has come. Congratulations on the adoption on the cloud setting as well. Looking forward to it. Quick question, do you think trifactor is available in an academic edition for use in a course if we create a data engineering course?
So two things. One, anybody can sign up for an academic account for free. It's a cloud service. So just go to trifactor.com and then there's a button that says start wrangling or give it a try or something like that. And then just click the I'm an educator or a student and you'll get a free account. For courseware, what I'm learning this semester is there's some features I'd like as an instructor that are not, our enterprise customers haven't been asking for, like, you know, assignment management. So I think it's got a ways to go to be a really good educational tool, but let's talk. It's definitely usable, but you want to use it in concert with other things.
Happy to connect offline about that. So students, any last questions from anyone for Joe? Oh, we have a hand raised from.
All right, so let's do this. Let's let everyone go.
Yes.
Nice to see you folks, and then we'll do a conversation.
Yes. Thank you folks for joining. Siddharth, yes, one last question.
How scalable is, I guess, trifactor to bigger data? Is it can you save clean in trifactor and then export it as like a clean CSV file?
Yeah, so trifactor actually from the beginning, because it's doing software program synthesis, that Wrangle script that you saw on the right, that's our internal domain specific language. And then we can compile that down to various other languages. So Spark is one of the default things that it'll compile down to. So if you're running, the point is our customers aren't even aware of this, but under the covers, if you're running on AWS, it'll run it in Spark and scale with Spark. If you're running it in Google, it'll run it in Google Cloud Dataflow, which is their Spark-like object. And what's coming down the pipe in a month or two, and I'll steal some thunder from our marketing department, is exportable pandas or SQL scripts. So you'll be able to, instead of compiling it down to an engine and just getting the data out, if you prefer, you can get the code out in a language that's more standard than Wrangle.
Okay, that's cool. Thanks.
Yeah.
Thank you, Doug. So with this, I will end the recording. Thank you to the audience for joining and for the questions. I will stop the recording now.